Okay, so we have finished the section on translational motion and the quantum mechanical description of translational motion, dealing with the particle in a box. And the next type of motion that we are going to consider is vibrational motion. This type of motion is also known as harmonic motion. And this type of motion is the motion that a particle undergoes when it experiences a restoring force proportional to its displacement. So this is typically when something is connected to a spring. So when it moves further away from the point of attachment, the spring starts to pull it back towards the point of attachment. And that's why we say it has a restoring force, and this force is proportional to its displacement, because the further it's displaced, or the further the spring is compressed, the stronger this restoring force. Just one thing in terms of the harmonic oscillator system, one thing that you need to remember for the system, it is at the turning points. So when your position, x, is equal to the turning points, all the energy is equal to potential energy. And there is no kinetic energy. So the kinetic energy is equal to 0 at the turning points. And as the object oscillates, for example like this, there is a change between potential energy being changed into kinetic energy the whole time, but at the turning points, for a millisecond, the object's actually standing still, so there's no kinetic energy, only potential energy. And your potential energy is, of course, the spring that is compressed. So please remember this. At your turning points, so where your oscillator turns around, there's only potential energy, no kinetic energy. One can express the equation that describes the force that is experienced in terms of that, and K is known as the force constant, whereas X is the position of the oscillator. And this force constant tells us how stiff the spring is. And the stiffer the spring, the larger the K. So I would recommend that you do a bit of self-study on the classical mechanics of this system, if some of this is a bit foreign to you, so please spend some time on that. What is important in this system is the potential energy equation. For a oscillator, harmonic oscillator, the potential energy is given to by half kx squared. And this is what the potential energy well looks like. So we have parabolic potential energy well. So this is our equilibrium position at 0, and this is this displacement x relative to the equilibrium position. And the higher or the larger k, the narrower this well. So for a small k, the potential energy well will have a shape like that, and for a very stiff spring, the potential energy well will have a shape like this. So this is for a large k, stiff spring, small k or small force constant, a weaker spring. So what does the Schrödinger equation for this particle look like? Well, we can start with the general form of the Schrödinger equation that you're all familiar with, and in the place of the potential energy, we just substitute half kx squared, which is the potential energy for the harmonic oscillator. And if you do that, you find the Schrödinger equation for the harmonic oscillator system. So solving the Schrödinger equation provides us with both the energies and the wave functions of the harmonic oscillator. And we're going to look at the energy levels first. Again, the energies are quantized as a result of boundary conditions. And these boundary conditions are basically that the oscillator will not be found with infinitely large compressions or extensions. You can imagine if something is connected by a spring, the spring can only stretch so far, and then it brings the object back. So that distance is limited. So there are some boundaries. So at some point the wave function has to go to 0 because the object will not be found at that distance. So if we look at the expressions for energies, and I'm going to ask you to assume these equations, we're not going to derive them or prove them. They look as shown there in that equation. Now the first thing you'll notice is that we have a couple of new symbols. The first one, which is our subscript there, and it also appears in the equation, looks like a V, and that is the Greek symbol called upsilon. Now don't confuse that with the symbol mu that we use for frequency. And this is the quantum number that we are going to use for the harmonic oscillator system, the quantum number upsilon. Because we're working with a new system, we're introducing a new quantum number. For the particle in a box, the quantum number was n. For harmonic oscillator, the quantum number is upsilon. Remember, I suggested that you guys put together a table listing all the different parameters for each system. So now you can also add a column for quantum numbers and add the new quantum number for the harmonic oscillator system. We see h bar again, and we also see another symbol that almost looks like a W, and this is the Greek symbol omega. Okay, so what do all of these symbols mean? Well, omega has to do with the force constant K and the mass of the particle. And also very importantly, the quantum number upsilon in this case is allowed to take the value 0, and it runs from 0 up to infinity. So that's different from the particle in a box system where 0 was not allowed. So just think about your energy levels. If we were to talk about the ground state, in this case the ground state is the upsilon equal to 0 level. First excited state would be upsilon equal to 1. Second excited state would be upsilon equal to 2. These quantum numbers were different for the particle in a box system, where your ground state was n equal to 1. And your first excited state was n equal to 2. Second excited state n equal to 3. So you can see that these numbers are different for the two different systems. Okay, so this energy expression I just want you to assume and know that omega is related to the force constant and the mass of the particle. We'll notice that omega is directly proportional to the force constant, so it increases with increasing force constant, and it's inversely proportional to the mass. Now let's have a look at the energy level diagram. So let's first calculate the separation between the two levels. So if you were to calculate the separation between level upsilon plus 1 and level upsilon, you get a value of h bar omega. And I want you to go and check that in your own time. See if you agree with that. And if you do that for any pair of consecutive levels, you actually find exactly the same value. So it's the same for any upsilon, and the epsilon plus 1 levels. So if we look at these energy levels, they form a uniform ladder. Remember, for the particle in a box system, the spacings increased with increasing quantum number. However, in this case, we have a uniform ladder. So if we were to plot the energy levels as a function of quantum number epsilon, I know in your textbook that looks like a V, but that's actually our quantum number epsilon. The spacing between epsilon 0, epsilon 1, 1, 2, 2, 3, 3, 4, etc. are all exactly the same, equal to h bar omega. Remember, we said the lowest quantum number gives us our ground state energy level. So that is our ground state. And again, I want you to notice that this is not equal to 0. So again, we have a 0 point energy. Question here, what is the spacing of the ladder? Well, that is equal to h bar omega. Now, if we look at the effect of mass on the spacing, remember omega has to do with mass. Omega is inversely proportional to mass. So the larger the mass, the smaller omega. So h bar omega becomes very small when mass is large. So for a small mass, the spacing is significant, but for a large mass, the spacing becomes insignificant. So again, the spacing is important for small objects, which is true for quantum mechanical objects, microscopic objects, and not the macroscopic world that we live in. Okay, so we have mentioned the fact that there is a 0 point energy for the harmonic oscillator, and one can calculate what that 0 point energy is by looking at the energy equation, which is equal to this, and just making mu equal to 0, epsilon equal to 0. So it's a half h bar omega, which gives us that value. So that is the 0 point energy. So again, we can ask the question, well, why is there a 0 point energy? Why can't the energy be equal to 0? Well, mathematically, if we look at this equation, to have an energy of 0, epsilon has to be minus a half, because minus a half plus a half will give us 0 times h bar omega, which would be 0. And we know that we don't allow epsilon non-integer values or negative values. So mathematically that's not allowed. Our physical reason is very similar to that given for the particle in a box. Again, the particle is not confined. We know it is confined to a specific area because it's attached by a spring. So the position is not completely unknown, so the uncertainty in the position is not infinite. So its momentum is not completely known. Uncertainty in momentum is not 0. So the momentum cannot be 0. Kinetic energy cannot be 0. It must have kinetic energy. The energy cannot be 0, so there has to be a 0 point. So how do we apply the harmonic oscillator model to chemistry? Well, if you think about atoms and molecules, atoms in molecules vibrate relative to one another, and one can consider the bonds between atoms to behave like springs. So we can use this energy equation that we've just defined to calculate vibrational energy levels of a specific bond. For example, a hydrogen atom bonded to another atom. And we're going to look at a specific example calculating this. So calculating a molecular vibrational absorption frequency. So this means you have an atom that vibrates, a molecule that vibrates in a specific way, and then it absorbs a photon and it goes to a higher vibrational energy level and it vibrates faster. And remember, these energy levels that we are talking about is the energy ladder that we defined earlier. So let's say initially your molecule is in the ground state vibrational state, so it vibrates slowly. It then absorbs a photon and it goes to the first excited vibrational states and it vibrates faster. So we're talking about vibrational energy levels. This doesn't have anything to do with electronic energy levels. We're talking about vibrational energy levels. And we're going to basically calculate where a specific molecule will absorb. So in this example, we have a heavy atom X which forms a stationary anchor for the very light hydrogen atom. So there's our heavy atom X and there's the light hydrogen atom. Only the hydrogen atom moves, vibrating as a simple harmonic oscillator. Okay, so the question in this case says that it's a harmonic oscillator, but just from the word vibrating, you should know that you should use the harmonic oscillator model. So that information will not always be given. You're given the mass of a proton, which is the mass of your hydrogen atom, and also K, which is the force constant for this spring. First part of the question, calculate the separation of adjacent levels. So these are energy levels. And then second part of the question, if vibration of the bond from one level to the next is caused by a photon, calculate the frequency and the wavelength of the photon required. Okay, so let's have a look at the first part of the question. We want the separation of adjacent levels. So we've seen this equation before, stating that the separation is equal for any two consecutive energies. But we also know that omega is equal to that. So we can calculate omega using the force constant and the mass. And you can get an answer for that. Okay, but obviously these units need some work, and what we know is that 1 Newton is equal to 1 meter kilograms second to the minus 2. This you'll find in your data sheet. So let's do that substitution. So that's a meter. Okay. That cancels with that. That cancels with that, and that is per second. So H bar omega there we have the energy level separation. So remember, this is the difference between two energy levels. It's not the energy of the level, it's the difference between the two energies. So we can call it the delta E. Okay, and the second part of the question says if vibration of the bond from one level to the next is caused by a photon, what is the frequency and the wavelength of the photon required? Let's look at the B part of the question. Well, we know that the energy of the photon should correspond to this delta E. So the energy of the photon is equal to h nu, which is equal to 5.7 times 10 to the minus 20 joule. So nu is 5.7 times 10 to the minus 20 joule divided by h. So there's the frequency. To get the wavelength, you can use that equation. So there's the frequency and the wavelength of the photon required for this transition.